we are going to revisit tangents a little bit. We did tangents a couple of sections ago, and we're going to revisit those here a little bit. All right, so here's what we did, right? We took a curve, picked a point P, and we're interested in the tangent line, call it T, at P. Let me move P down here. P, my tangent line got off a little bit. All right, so let's say the P is right there. Okay. How did we find the slope of that tangent? Well, we took a Q point out here, starting with, I'm taking it way out here just so I took a Q out there and figured out the slope of that secant line, right? So MPQ is the slope of the secant line. And so what I did was then I took those Q points closer and closer and closer in to P here, and eventually that would narrow it down to the slope of T, right? That's how I determined what the slope of my tangent line was. Okay, well, if let's say my function is function f, point P, the x value is a, and then Q, I'm coming out here to whatever x value I want. So I've got point P is a, and then the y value would be f of a, and Q would be f of x. The way we did it before, though, was using a table, right? We set up a table, and we let the x value vary as we got closer. We wanted, say, a was 1, then we let x come in closer and closer and closer to 1, right? 1.01, 1.001, and so forth and so on, okay? And we set up our table and did MPQ. Now, what was MPQ equal to? We set it up, didn't we? Yeah, we set it up. We just took the difference of the y's over difference of the x's. y2 minus y1 over x2 minus x1. I don't know that we wrote it in general like this, but this is what it looks like. You know, whatever your function value is, f of x, whatever it is, this is what the slope of that secant line would be, MPQ. Okay? Well, why we're revisiting that now is because now we have nice ways, instead of using a table here, tables are going to be out for this section anyway. We'll still do a couple of tables. It'll still be on the test, but we now have more direct routes to find this slope of the secant line, slope of the tangent line by using these secant lines. Here's how we do that. What we did was, we, like we said, we drew in, we let the x come in closer and closer to a. Well, isn't that our limiting process? So here's what it amounts to. The slope of the tangent line equals the limit as x approaches a of this secant line formula. I mentioned that it was kind of a limiting process, but now we're going to formally go there and actually evaluate some of these without using a table. We're going to find the slopes of tangent lines without using tables. We're going to use instead limits. So the slope of the tangent line equals the limit of the slopes of the secant lines, basically. That's what this amounts to. The slope of the tangent line equals the limit as x approaches a of the slopes of the secant lines. Because as you get Q closer and closer in, your slope gets closer and closer to the tangent slope. Okay? This is what they call definition 1 of slopes of tangent lines. So if they refer to definition 1 or I refer to definition 1, that is what we refer to. Okay? All right, so let's see how it is in action here. Is that okay? Any question about what I'm saying there? Basically, what we were doing is that we're sticking a limit on it, on the thing that we come up with as far as the slope is. Okay? All right. So using definition 1, find the slope of the tangent line for y equals x squared at the point 3, 9. Definition 1 again says that the slope of the tangent line, m, equals, so the limit as x approaches a, f of x minus f of a over x minus a. Okay? First of all, which is my a? This is my a right here. A is just the point, the x value of the point that I want to find the slope of the tangent line at. So a is 3 here. So I have the limit as x approaches 3 of f of x. Let's just go ahead and replace a by 3 everywhere. So everywhere I have an a is 3, so I'm replacing it by 3. Okay, well, now that remains here is just to do the rest. What's f of x? F of x is kind of the varying function value here. Well, they say it's y equals f of y equals x squared, but that's synonymous with f of x equals x squared. This is f of x right here, right? Same thing. Y equals x squared, f of x equals x squared. Same thing. So what is f of x here? It's the x squared. Now, f of 3, well, that's going to be the function value evaluated at 3. So what is f of 3 here? Well, f of 3 would just mean plug in 3. So it'll be 3 squared, which is 9, which of course I've already got right there. So is everybody with me? Where f of 3 is 9? And then the bottom is just x minus 3. Okay, well, voila. Now we have limits that we've done. Haven't we done these limits now? We've done this sort of limit before. How do I do this limit? Factor it, cancel, evaluate, right? Yeah, this is now just a plain old limit that we've been working on. And so we get the limit as x approaches 3 of, that would be x minus 3x plus 3 over x minus 3. Factor the x squared minus 9. The x minus 3's cancel. We couldn't evaluate this limit yet because 3 gives me a denominator 0. But now I've canceled the x minus 3 out, so now I've got the limit, don't I? Limit here is just 3 plus 3, that's 6. But now it takes on the added meaning because what does that tell me? That's the slope of my tangent line at 3, 9. The slope of this tangent line at 3, 9 turns out to be 6. Didn't use a table, didn't have to, because now I know something about these limits, so if I set up this limit, I can figure out the slope of the tangent line. And it's 6. Okay? All right. The f of 3? Yeah. It's because, yeah, it was the function is x squared, so you square the 3 to get 9. All right. So that is definition 1. And it is important. And you will have to do more of those along the way using definition 1. However, I also wanted to show you another one, sort of the same idea, a little different way of thinking about it, I guess.